Hey guys, so this is Colton. So I thought that with some of you that are working on some embedded software drivers, you're looking to probably start kind of trying to deploy your code to the hardware and doing some tests soon. So I thought I would kind of make a quick video going over the ways in which we can actually test these drivers that you're developing. So there's essentially three different ways that we can do that, one of which is via the terminal application program, which is what this flowchart is showing. One way is through unit testing, and another way is through actually using the on-chip debugger and stepping through the code using GDB. So I'll actually probably make videos on all three of these things right now. I'm just going to go over the actual terminal program. Um, so definitely unit tests will be very useful because you can actually implement them on your PC machine. You don't actually need any embedded hardware, whereas these other two methods of using the terminal application as well as stepping through the code on GDB with GDB actually do require the hardware. So with that being said, so now we're going to talk a little bit about this terminal program. So it's actually two different programs, one running on the embedded side and one running on the PC side. So the embedded is a C that you guys have been developing, and then the PC side is Python via this SDEC program. So if you haven't already, go over to GitHub and clone this SDEC repository. So here you can see all of the documentation on the various commands that have already been implemented, as well as all of the different options and subcommands and whatnot. And then obviously for all of the firmware repositories, as you've probably already seen, we've been developing everything in this terminal folder, as opposed to this flight folder for the flight computer or the hot fire folder for the engine controller. And so basically this terminal program, the idea of it is just to give us a terminal interface to our embedded controllers that allow us to basically access any of the hardware, as well as test the low-level drivers. And so kind of when you come into this terminal directory, you see here's where the main .c and main.h files are that contain our application code. And then there's the mod folder, which contains all of your code, as well as the config folder, which contains just very basic microcontroller configuration code, most of which is actually auto-generated, as well as this auto folder, which is the actual auto-generated code. So to kind of go into how this terminal program really works, so you kind of start with the Python program running on your PC, and essentially what you get is this prompt that allows you to enter commands. You enter in a command, and then the Python program parses that command. So it extracts what the command is, what the subcommand is, what the options are, stores all of the options, all of that fun stuff gets handled here within the SDEC program. And once that processing happens, then a connection is established with the embedded board here, and that is done over USB using the PySerial library. Within the SDEC program, there's actually a wrapper for the PySerial serial object, so you'll just be calling that object and calling methods on that object to actually communicate with the boards over USB. But once you send the data over USB, then it goes to the embedded controller, and the flow transitions to the embedded C. So basically, the way that the terminal program works on the embedded side is that you have this essentially really big switch case statement that looks at what this. You have a command opcode that gets transmitted first. The C program receives that opcode, passes it to a switch case statement, and that switch case statement determines what command it's going to be run, or what command is running. Then once you get into that switch case statement, you get further parsing for subcommands and options. So You may or may, based on what you're trying to implement, you may have to get some more data from the USB port. And then once you've received that data, then you pass it to this function, which starts with the module prefix and then it's CMD execute. And basically what that does is it takes in some type of subcommand opcode and potentially additional data. And from that information figures out which module API function it needs to call. So then once that function gets invoked, it will then call an API function that we're trying to test. That API function will be executed, and the result will be returned to that call mod or to that mod CMD execute function. Once you get that result, then that result gets sent back to the Python program, and then the Python displays it on the console, and then it just goes in a loop, so you just can type in as many commands as you wish. So to kind of show you what that looks like, if you haven't already seen it, so you can see on the right here, I have my Python program being run. I'll actually just exit out of that and then go back into it. So there's my Python program, and there's my little prompt in which I can enter commands. So like help, for example, will display all of the different commands and options. It's kind of hard to see that. So if you full screen that, you can kind of read through it, and if you forget what the options are or subcommands are, you can look at that. Anyway, hold on. Let's clear that terminal, and then go back to this is actually the firmware repository for the engine controller. So you can see I'm in the terminal directory for Rev4 of the board, which is the one I have on my desk here hooked up to my computer. So I can, let's see, I'll just clean that out and I'll recompile the program. That'll take a second to compile. Once it's compiled, then I will flash it to the hardware. Okay, so now the engine controller has that terminal application on it. So if I go back over to my Python terminal, I can start typing commands. So one of the basic commands is the com ports command, and this command was one of the first ones I implemented just to help me figure out which com ports the embedded boards would be connected to. So if you run com ports -l, that'll list all of the available com ports that the PySerial module sees. And as you can see here, I have two. The second one is obviously my board, as the CP2102 USB to UART bridge controller is the chip on both the flight computer and the engine controller that allows our microcontroller to communicate over USB. So now that I know what port I'm on, actually I can connect to it. So I can run com ports -c for connect, and then I type in the name of the port, and then the baud rate, which is 9600 for everything right now. And you can see I'm connected to the port, and then I can run a command like ping. So if you run ping -t for timeout, we'll run ping with a timeout of 1 second. And if you run that, you can see that I actually pinged the engine controller, and it told me how long it actually took. So if you didn't know what board it was or what revision of the hardware you were working with, you could run the ping command after connecting to the serial port. And then, of course, you can also just disconnect with the -d, which we'll need to actually run the more useful connect command. So if you already know what board you're working with, you're going to want to run the connect command, -p for port, and then the name of the serial port, and then you connect to the board that you're actually physically attached to. And so the reason why you do this is so that you can run command, or you can run board specific commands. As the way that the current program is set up is if you try to run a command for the engine controller on the flight computer, it's gonna throw an error at you. It won't let you do it. So you have to run this connect command first to establish a valid connection with the board before you actually run board specific commands. But now that I'm connected to the board, I can run all sorts of commands. Like, for example, I could run power source, tells me where my power supply is coming. And as you can see, it's coming from USB, obviously, since it's hooked up to my computer. You can look at the ignition continuity stats. You can run ignition oh, okay. Well, maybe it's ignite cont. So ignite cont for continuity will show me which ignition terminals of my controller currently have continuity in them, and you can see that all of them are disconnected except for the E match and switch, which that actually is also disconnected. That's just a slight bug in the hardware, but I think the point gets across. So there's also the sensor command, which will be relevant for many of you for displaying sensor values. So sensor dump, for example, just pulls all of the sensors on board once and displays the data to the terminal. So you can see I got all of the sensor readouts here, and obviously they're all coming out as 0 because I don't have anything attached to the board right now. But yeah, so that's the basic idea of the terminal program. And so if we can look at the code here so I can kind of explain what I was talking about earlier. So to start out with the embedded side of things, you can see we've got our includes here, function prototypes, configuration stuff. And then when we get down to the event loop here, this is where the code for that you'll have to implement is to test the modules that you've been working on. So you can see the way it works is it first pulls the USB port using the microcontroller's UART to get the opcode, and then it goes into, well, first it checks if there's a timeout. If there's a timeout, it doesn't do anything, which just means you haven't sent a command or anything like that. But then if it wasn't a timeout, if there is valid data on the USB port, well, then you go into this switch case statement using that data variable. That's not a very descriptive name. I'm probably going to change that, but that's what it is right now. So you go into the switch case statement where the case you're looking at is the opcode for the command. So as you could see, I ran a couple different commands there. Like ping has an opcode, connect has an opcode, ignite has an opcode, and so whichever opcode gets received by the embedded code determines which of these switch case statements it goes into. So for some of the simpler commands like ping, you can just literally call the API function directly. Whereas for some of the more complex commands like the ignite command, you can see that I actually am going into this ignition CMD execute like I was talking about earlier. So for this more complex command, since it does have subcommands, the first thing you do is you pull the USB port for that subcommand. Then once you get the subcommand, you pass it to this ignition CMD execute function that figures out which API function to call, and then basically it just transmits a response. So that's about it. So you can see it's about the same for all of these other switch cases. So I can actually go and show you what the CMD execute command looks like. But yeah, okay, let's go into the ignition module, and I want to just show you real quick what that CMD execute function looks like. So here it is. So basically you can see the only input to the function is the ignition subcommand. Since the ignite command only really has a subcommand, it doesn't have anything more complex than that. So you just have the subcommand get passed into that function. And then what basically happens is you get another switch case where if you have the ignition fire code, then you call this API function ignite. Whereas if you get the continuity code, you call this function get continuity info. And then if you get some random subcommand, you invoke the error handler. And then the ignition status variable is returned by the API functions, and that will tell you whether or not the function was executed normally or not. And then that's what ultimately actually gets sent back to the SDEC program. And so if the SDEC program gets a weird status code, it will display the necessary information to the terminal so you can know why the API function failed. But anyway, that I think that's about it for the embedded side of things. I do want to show actually one more thing, which is the sensor module, because a lot of you will actually be working with this directly. And so the sensor module is a little bit special just because there's going to be multiple different sensors on each board, each of which will have its own driver, whereas the sensor module is actually kind of integrating all of those modules together into one. So the sensor module for the flight computer is gonna contain both the IMU, the GPS, and the baro sensor. So you know when you're working on those um, when you're working on those drivers, that CMD execute function is actually going to be in the sensor module, not in IMU.c or baro.c or GPS.c. Um, so just hold on, just going into that real quick. So you can see I'm including my pressure module here. So far, I actually don't have the other ones yet. It's just pressure, but there will also be like load cell, thermocouple here as well. And then you go, here's that sensor CMD execute command. And so it takes in, as before, it takes a sub command in as an input. It's got a couple different local variables here for kind of manipulating the ways the sensor data is stored in memory. And then what it does is it goes into the switch case statement as before, based on what the sensor subcommand code was. And then you can see here it actually figures out how to call the API function. And then this sensor dump API function actually calls the API functions in the pressure module, whereas for the flight computer, it will call both the IMU driver and the barometric pressure sensor driver. So that's just something to keep in mind. And then it just transmits the data that it receives back to the PC. And then it reports the status of the command back to the Python program. So that's just kind of a quick overview of what the function or of what the code does. So obviously, I don't expect you to just understand based off. I don't expect you to understand everything based off of a 15-minute explanation of the code, but hopefully that's helpful. And if you spend some time looking through the code, I hope it will make sense. So last thing, I guess I'll go over the Python code a little bit. So like the Python code is organized as so there's like the SDEC.py script, which is kind of the very high level code, whereas there's commands.py, which contains implementations of command functions that apply to all of the boards. So like ping, for example, connect, those all apply to all of the boards. So those will be in commands.py. And then engine controller, valve controller.py, those contain functions specific to the engine controller board and the valve controller board. So if we're needing to implement commands specific to the flight computer board, we're going to actually have to create a new Python file that's called flightcomputer.py or something like that. But to go into sdec.py, you can see here we got a bunch of imports, obviously importing all of those other Python modules. And then we have a list of commands here. So this is kind of the global command list. So these are actually all of the different commands that are currently implemented. So if you need to make a new command, you need to add it to this list, and then just link it to the correct function in the correct file. So then you have the serial object wrapper that I was talking about, which I called terminal data for some reason. So you can see this actually contains the PySerial serial port object and a number of helper functions to do things like initialize the COM port, configure the COM port, open a COM port, close it, check to see if it's active, listing ports and sending bytes. That's interesting. I don't know why there's two send bytes. I guess I'll have to look at that later. I'm not sure how that happened. But anyway, and then there's read byte and setting controllers. So most of this stuff you probably won't need to touch, but it's here just for reference in case you need it to. Well, except for obviously sending and reading bytes. So these methods you will probably use quite often. Parse input, I'll get to that in a second. And then this is the full application loop. It's only like 10 lines of code. Basically, you display the prompt, you get the input from the user, you clean it up, then you separate the command from the command arguments, and then from that command list I was talking about earlier, you figure out which function to call, and then you pass it in the arguments that were supplied on the command line as one input, and then that serial object wrapper that I was talking about just now is also passed in. And basically, the serial object wrapper gets passed around all of the functions, so that contains all of the global data that might need to be shared between functions. And then this parse input, like I said, just basically cleans the data that you enter into the command prompt. So to kind of go into what some of the commands, so all of the commands, like sensor, for example, is a command, gets implemented as a function in one of these files. So you can see here, if I search for sensor, I can find this function called sensor, which gets called by SDEC.py, as I just showed you. And so the typical implementation here is you store all of the various types of inputs in a dictionary. You set the maximum arguments that the function might expect. You specify whether the command type includes subcommands or not. You include the opcode, which is what gets originally sent to the embedded controller, as well as subcommand codes, and then just buffers for data. Then you do some input parsing, which you can call this parse args function, which does a bunch of very basic checks on the data. Then you split up the data into like subcommands, options, inputs, stuff like that. You do some command-specific checks. So, for example, in the case of sensor, like a command-specific check that you might do is like, did the user supply a sensor that doesn't exist? Obviously, you can't check that on every function because not every function includes sensors, so that would go in that section. And then you get to this big if statement here, which actually calls a different block of code based on what the subcommand was. So you can see sensor help here displays help info. Sensor dump here, this is a relatively large subcommand here, which sends an opcode telling it it's sensor. Then it sends that subcommand code. Then it actually reads data from the engine or from the embedded controller, and then all of this code just prints it to the terminal in a fancy way. So, and that's about it. So, and every time you execute one of these subcommands, you return that serial object wrapper, which then just gets passed around to whatever gets called next. So yeah, so that's about it. So I'll probably be following this up later with a video on using GDB and also writing unit tests, but for now I'll call it here. So hopefully we'll be able to actually implement a lot of this stuff for the drivers that you guys are working on. But in the meantime, if you have any questions on this or if anything wasn't clear, please do not hesitate to reach out. But yeah, that's it.